Hey there, science fans! Welcome back to another exciting episode where we unravel the mysteries of the scientific world. Today, we're diving into the fascinating world of titration, a process that might seem complex but is incredibly intriguing once you get the hang of it. Titration is a fundamental technique used by scientists across various fields, from chemistry to biology and even environmental science. This method helps us determine the unknown concentration of a solution, which is crucial for many scientific analyses and experiments. Think of it as solving a complex puzzle, where we carefully add one solution to another until we reach a perfect balance, known as the equivalence point. Imagine you have a beaker filled with a mysterious liquid, and you need to know exactly how much of a specific substance is dissolved in it. This is where titration comes into play, providing a precise and reliable method to uncover the secrets hidden within that liquid. By slowly adding a solution of known concentration, called the titrant, to the unknown solution, we can observe the reaction and determine the concentration of the unknown substance. The process involves careful measurement and observation, ensuring that each drop of titrant brings us closer to the answer. As the titrant is added, we note down the changes, such as color shifts or precipitate formation, which indicate the progress of the reaction. But titration isn't just confined to earthbound labs. This versatile technique has even found its way into space exploration. It has journeyed to other planets like Mars, where it plays a crucial role in analyzing extraterrestrial materials. The Phoenix Mars lander, a robotic spacecraft, used titration to analyze Martian soil and search for signs of life. How cool is that? This shows the incredible versatility and importance of titration in expanding our understanding of the universe. So next time you think about titration, remember it's not just a lab technique. It's a key to unlocking the secrets of solutions, whether on Earth or on distant planets. Stay curious, keep exploring, and who knows? Maybe one day you'll be using titration to make groundbreaking discoveries of your own. Are you enjoying the video so far? Subscribe so that you ace that chemistry class. And if you like learning about chemistry for fun, regardless of why you clicked on this video, subscribe so you never miss any future ones. I will provide a link to the textbook down in the description below. This textbook is the source of all my videos and lectures, and where the information comes from for my analytical chemistry videos. Let's get back to the lecture. Titration falls under a broader category of chemical analysis called volumetric analysis. This technique relies on precise volume measurements to determine the amount of a substance. Think of it like baking a cake. You wouldn't just throw in random amounts of ingredients, right? You carefully measure each one to get the perfect consistency and taste. In titration, we use a special piece of glassware called a burette. This long, graduated tube allows us to add the titrant drop by drop to our unknown solution. By carefully monitoring the volume of titrant added, we can calculate the exact concentration of the substance we're interested in. Volumetric analysis, particularly titration, plays a crucial role in various fields. From determining the acidity of our oceans to ensuring the quality of our drinking water, titration helps us understand and control the world around us. Now, before we jump into the specifics of how titration works, let's talk about the key players involved. Titration is a fundamental technique in chemistry, used to determine the concentration of an unknown solution. But to perform a titration successfully, we need to understand the essential components and their roles. First, we have the analyte, which is our mystery solution with the unknown concentration. The analyte is the substance we want to analyze, and it could be anything from an acid to a base, or even a complex ion. The goal is to find out how much of a particular substance is present in this solution. Then comes the titrant, a solution with a precisely known concentration that we add to the analyte. The titrant is carefully prepared and standardized, meaning its concentration is accurately known. This allows us to calculate the concentration of the analyte based on the volume of titrant used. But wait, there's more. To know when our titration is complete, we need a little helper called an indicator. Indicators are substances that change color at a specific pH level, signaling the end of the titration. They are crucial because they provide a visual cue that the reaction has reached its endpoint. An indicator is a substance that changes color depending on the acidity or basicity of the solution. Different indicators change color at different pH levels, so choosing the right one for your titration is essential. For example, Phenolphthalein turns pink in basic solutions, while methyl orange changes from red to yellow in acidic to neutral solutions. It's like a traffic light, signaling us when we've reached the desired point in our reaction. Just as a traffic light tells drivers when to stop or go, an indicator tells us when the titration is complete. This visual change is what makes titration such a precise and reliable method. Finally, we need a suitable reaction between the analyte and the titrant. The reaction should be well-defined and stoichiometric, meaning it follows a specific ratio of reactants to products. This ensures that the amount of titrant added corresponds directly to the amount of analyte present. This reaction should be fast, complete, and easily observable. A fast reaction ensures that the titration can be performed quickly, while a complete reaction ensures that all of the analyte reacts with the titrant. An easily observable reaction, such as a color change or the formation of a precipitate, makes it easy to determine the endpoint. We want to see a clear change like a color change or the formation of a precipitate to indicate the endpoint of our titration. This clear change is what allows us to accurately determine the concentration of the analyte. By understanding these key components and their roles, we can perform titrations with confidence and precision, unlocking the secrets of our mystery solutions. Finding the balance equivalence point versus endpoint. Now, let's talk about two important concepts in titration: the equivalence point and the endpoint. The equivalence point is the theoretical point at which the titrant has completely neutralized the analyte. It's like finding the perfect balance between two opposing forces. However, in practice, it's difficult to determine the exact equivalence point. Instead, we rely on the endpoint, which is the point at which the indicator changes color. The endpoint is a visual cue that tells us we're close to the equivalence point, like playing darts. The equivalence point is the bullseye, and the endpoint is where our dart lands on the board. While we aim for the bullseye, hitting close to it is still a good shot. A world of reactions, common titration methods. Titration is a fundamental technique in chemistry, used to determine the concentration of an unknown solution. It's a method that has been refined and perfected over centuries, and today it remains a cornerstone of analytical chemistry. Titration isn't a one-size-fits-all technique. Depending on the nature of the chemical reaction involved, different types of titrations are employed. Each type has its own unique procedures, indicators, and applications, making titration a versatile and indispensable tool in the chemist's arsenal. There are various types of titrations, each based on a specific chemical reaction. These include acid-base titrations, redox titrations, complexometric titrations, and precipitation titrations. Each type of titration is designed to exploit a particular kind of chemical interaction, allowing for precise and accurate measurements. Let's explore some of the most common ones in detail. Understanding these methods will give us a deeper appreciation of the science behind titration and its practical applications in various fields, from pharmaceuticals to environmental science. Acid-base titration. This classic type of titration involves neutralizing an acid with a base or vice versa. It's one of the most straightforward and widely used titration methods. The process typically involves adding a titrant of known concentration to a solution of unknown concentration until the reaction reaches its endpoint, which is often indicated by a color change. It's like a chemical tug of war, and the indicator helps us determine the winner. The endpoint is reached when the amount of titrant added is stoichiometrically equivalent to the amount of substance in the sample. This method is commonly used in industries such as food and beverage, pharmaceuticals, and water treatment to ensure product quality and safety. Redox titration. In this type, we're dealing with the transfer of electrons between reactants. Redox titrations are used to determine the concentration of an oxidizing or reducing agent in a solution. The titrant is an oxidizing or reducing agent of known concentration, and the endpoint is detected using an indicator that changes color when the oxidation state of the solution changes. It's like passing a hot potato, and the indicator tells us when the potato has reached its final destination. Redox titrations are essential in fields such as environmental monitoring, where they are used to measure the levels of pollutants like chlorine and iron in water samples. Complexometric titration. This method involves the formation of a complex between a metal ion and a complexing agent. The most common complexing agent used is EDTA, which forms stable complexes with metal ions. The endpoint is usually indicated by a color change in a metal ion indicator. Think of it like a lock and key, where the indicator signals when the lock has been perfectly fitted. Complexometric titrations are widely used in water hardness testing, where they help determine the concentration of calcium and magnesium ions in water samples. Precipitation titration. This type involves the formation of an insoluble solid called a precipitate when two solutions are mixed. The endpoint is reached when the amount of titrant added is sufficient to completely precipitate the analyte from the solution. It's like watching a cloud form in a bottle, and the indicator tells us when the cloud is fully formed. Precipitation titrations are commonly used in the determination of chloride ions in water samples, where silver nitrate is used as the titrant to form a white precipitate of silver chloride. Each type of titration has its own set of rules and applications. The choice of titration method depends on the nature of the analyte, the required precision, and the available equipment. Understanding these nuances is crucial for accurate and reliable results. But they all share the same goal: to determine the unknown concentration of a solution with precision and accuracy. Whether it's ensuring the safety of our drinking water, verifying the potency of a pharmaceutical product, or monitoring environmental pollutants, titration remains an essential technique in the world of chemistry. As we wrap up our exploration of common titration methods, it's important to note that the world of titration is ever evolving. Advances in technology and research have led to the development of sophisticated titration techniques that offer even greater precision and efficiency. Let's take a closer look at some of these advanced methods and the innovations that are shaping the future of titration. Potentiometric titration. This advanced technique involves measuring the electrical potential difference between two electrodes in the solution. Unlike traditional titrations that rely on visual indicators, potentiometric titrations use an electrode to detect the endpoint, providing highly accurate results even in colored or turbid solutions. It's like having a digital eye that never misses a beat, making it invaluable in pharmaceutical and industrial applications where precision is paramount. Coulometric titration. In this method, the amount of titrant is determined by measuring the electric charge passed during the reaction. Coulometric titrations are particularly useful for analyzing small sample sizes and are often employed in the determination of trace amounts of water in substances. Think of it as a microscopic detective, uncovering hidden details with unparalleled accuracy. Thermometric titration. This technique measures the heat change during the titration process to determine the endpoint. Thermometric titrations are fast and do not require chemical indicators, making them ideal for reactions that produce significant heat changes. It's like having a thermometer that tells us exactly when the reaction is complete, streamlining processes in industries such as petrochemicals and food production. The future of titration holds exciting possibilities, from integrating artificial intelligence to developing new sensors and indicators. As we continue to innovate and refine these techniques, titration will remain a cornerstone of analytical chemistry, providing us with the tools to explore and understand the chemical world with ever greater clarity. In conclusion, titrations are a fundamental technique in chemistry that allow us to determine the concentration of a solution. By understanding the principles and methods of titration, we can achieve precise and accurate results in our experiments. Thank you for watching, and happy titrating! Like and subscribe. Make sure to share if you found this useful. Be sure to have a nice night, and good night.